lads next door said is operating air law in Oxford.
Yeah, it's scared, like we've been on
that takes a while.
this already what's going on.
Well, that's interesting because we had fairly reliable information that the only exam they changed in the last sitting was the comms. But we have other people say there's a few new ones in air law.
The ATP forum is saying about 20% in air law is new.
Right.
That was last night.
50% last week.
How much?
50% new question last week.
In air law?
Yeah.
Constant cat and mouse.
You get it.
Okay. Up until now, we've looked at when we've looked at circuits, we've only looked at resistance loads going in. If you've only got resistance loads in a circuit, then you have what's called a resistive circuit. Unfortunately, it's not that simple because you can also end up with facets of capacitance, inductance, which gives you problems of impedance and reactance. So we'll have a look at these. Now, a capacitor, you will recall from capacitance fuel measurement, consists of two plates across which we hold a charge and a dielectric or insulating layer between the two. If we apply a voltage to one plate, we get a positive on one side, negative on the other, and it holds that charge. Even if it's disconnected, it'll hold that charge until a circuit is created. So there are occasions where they need to put capacitors in a circuit for various purposes. They're very slow to charge, but they discharge very, very rapidly. They're useful in things like ignition units. So we can't avoid having capacitors in there. The symbol for a capacitor is very similar to the sketch diagram of a capacitor of two plates with a connection either side. We measure capacitance, you will recall, in farads after Sir Michael Faraday. Capacitance then is the property of a circuit or an element of that circuit that permits it to store a charge. That's all. Capacitive reactance is inversely proportional to frequency. The amount of reactance that capacitance gives us is inversely proportional to frequency. If frequency rises, the current flow will increase. 1 farad with 1 volt stores 1 coulomb of charge. Now the value of the capacitance, again harking back to the instruments exam, depends on the area of the plates, the distance between the plates and the material of the dielectric, whatever's between the two. And we'll recall, wouldn't we, that air was 1, fuel was 2 and water was 80. So just a different value of dielectric between them. So that changes the value of the capacitance. Now the maximum charge across the plates occurs when the supply current is 0 just before it reverses. The maximum discharge current occurs when the supply voltage is 0. And in a purely capacitive AC circuit, what you're going to get is the effect of shifting the current and the voltage out of phase. So literally, the voltage and the current are no longer in phase because of this thing called capacitive reactance. And I hear you saying, so what? What's that going to do to affect me? Stick with me and I'll show you where it takes you with capacitive reactance. The fact is that the current and the voltage are out of phase. Capacitors have low resistance to high frequencies. So logically they also have high resistance to low frequencies. Now that's capacitance. The other side of the coin is inductance. An induced current creates a field opposing the movement. It's something called Lenz's law, where a moving magnetic field is producing a change in current. It causes an induced voltage opposing the original change, much the same way as aerodynamic drag. If you think of inductance as electrical drag, and you won't be far off. It's also known as back EMF, a force opposing the original EMF. So the drag analogy is quite valid. Inductive reactance is proportional to frequency. So if the frequency rises, the current flow will decrease. And with inductance, 1 volt with a flow of 1 amp produces 1 Henry. It's Lenz's law, but Henry is the unit they use for it. I guess L was already used for something else. So when are we going to get inductance? Well, we're going to get it anywhere there's a coil. Motors, going to give us inductance. Generators, inductance. Electromagnets, transformers. Anywhere we've got a coil, we've got that back EMF being produced. Now, inductive reactance also shifts the current and the voltage out of phase, but it shifts it the other way. Inductors create high resistance to high frequencies, unlike capacitors, which have low resistance to high frequencies. Again, so what? Easy way to remember which way round it goes. In capacitors, the current leads the voltage, and the current lags the voltage in inductors. Civil. Capacitors, the current leads the voltage, and the current lags the voltage in inductors. The voltage is normally the datum, and we measure which has shifted from there, whether it's gone in advance of it or behind it. Even then I hear you saying, so what? Why does that affect me? What's the relevance? The relevance is power. The relevance is electrical power. I see the pen's still scribbling furiously, so I'll hang on for the next slide. All good? So, inductors, devices with coils in, and capacitors, devices that hold a charge, are behaving slightly differently in a circuit. With inductors, if they're in series, just like resistors, add them together. So L total is equal to L1 plus L2 plus L3, simple. So inductors behave like resistors. And if they're in parallel, it's the inverse, just like resistors. So if you can mentally link resistors and inductors in your head, then you're on the right track. You know that you're adding them together in series, and it's an inverse relationship in parallel. Capacitors, guess what, behave exactly the opposite. So capacitors in series an inverse relationship, and in parallel the sum. So if you can just remember to keep resistors and inductors together, you've got it cracked. Again, so what? Why do I even care? Why am I bothered? Well, I'm bothered because if I'm in a circuit that was purely resistive, that would be my amount of power that I'm producing or using. But capacitive reactance gives me a force this way. Inductive reactance gives me a force that way. Now, if I've got both capacitive and inductive reactance in a circuit, the capacitive reactance cancels out part of the inductive reactance and gives us the picture at the bottom. So it's a vector sum. The total reactance then is that side of the line of resistance, and the total reaction between them is impedance. Now you can see from that if you've got a circuit with lots of inductors in it, all you've got to do is put some capacitors in it and you balance each other out. That's what they do. Again, so what? Here's the so what. If everything's in phase in a purely resistive circuit, no capacitance, no inductance, the power is the sum of the voltage and the current, yeah? Power is volts times amps. So, there's the amount of power. The power is the sum of the blue line and the green line, which gives us the red line. If we put that out of phase, look what happens to our power peaks. Because it's a confused situation where the current and the voltage are out of phase, the sum of the two means we've got much less useful power. And if I just flick between the two, you can see how profound that difference can be. Same voltage, same current, but just putting them out of phase gives us a massive reduction in power. Now we see why we need to care about capacitance and inductance. Gives us the term useful power. Total power available is the vector sum of the two. The reactance load is wattless power, it's useless power, it's stuff that's no good to us. The useful power is on the vertical axis here. Reactance load, or it can also be, a capacitive or an inductive reactance load. It will move that line one side or the other, and the vector sum of the two is the total power. Not really the total power available, it's the total power we've got to produce to be able to have that much useful power. You'll also hear the terms kW, kVA and kVAR. Kilowatts is the real, true, active, effective or useful power. It's the actual power we can use from that system. kVAR is the reactive or wattless power. And kVA is the total apparent power. That's what it looks like we've got, but that's all we're actually going to get out of it.
Can you say those again, please?
Yeah, sure. Kilowatts is real power, the actual power, effective power. kVAR is the reactance load, it's wattless power. And kVA is the total apparent power. So in order to use that much, if we've got that much reactance load, we've got to produce that much. So that's why we need to care about capacitors and inductors.
So in an ideal situation, you want K rating to be where you can.
In an ideal situation, you wouldn't want any reactance load at all.
No.
And as I say, if you've got that much inductive reactance, all you've got to do is put some capacitors the other side, and that will drag that back to the middle, and then you're actually producing the power that you see is what you've got. Yeah. Frequency control. There's methods of controlling the frequency of an AC generator. The most basic is frequency wild, where you just let the thing, you don't control the RPM of the AC generator. The RPM is driven by the engine and it will just go up and down according to whatever speed the prime mover is at. No control of RPM. It relies on system resistance to use up any power that's produced unnecessarily. So really it's only useful for stuff that's high load. Things like heating, anti-icing, certain types of lighting could cope with frequency wild. But most of the time it's no use to us. So what we tend to have is constant speed drive units. Now in fixed wing aircraft, gas turbine engines, you're going to need to run a constant speed drive unit because your RPM isn't constant throughout your flight. For helicopters, of course, it's that much easier because the NR, the rotor speed, tends to be governed. So we'll run our generators off of the gearbox drive, and we've got a constant speed unit right there. But for fixed wing, you'll need a constant speed drive unit. Constant speed equals constant frequency. The other way to do it is variable speed, constant frequency, except that you can have a frequency wild output, but then you rectify it to DC and invert it back to a constant frequency AC. We mentioned paralleling of DC generators. If we try to parallel AC generators, we have to do that by adjusting the torque on the constant speed drive unit. It's a bit of a task. And it's not just speed, because when you're paralleling AC generators, the voltage, the frequency have got to all be in sync, in perfect sync. Otherwise you just will have a confused sine wave. CSTU, something like that. There's your gas turbine engine. From the gearbox drive, we're driving the constant speed drive unit shaft. There's a disconnect on it. They're fairly old hat, but they're still used. There's normally dire warnings on the panel that say, you know, disconnect it in flight, you can't reconnect it. And it works on the principle of two hydraulic motors. One with a fixed swash plate, one with a variable swash plate. So that gives us the means to have a constant output from a variable input. If that makes any sense.
So Chris, just say that again.
Yeah. This is two hydraulic motors inside the CSD, right? Constant speed drive unit. If you remember the two types of hydraulic motors we had, hydraulic pumps we had. One was a variable swash plate, and the other one was a fixed swash plate. So if you've got one that's variable and one that's fixed, you can have a constant speed output from a variable speed input. Yeah? So it's literally two hydraulic motors in one unit. And again, a quill shaft there so that a seizure in the generator is not going to trash the gearbox. Couldn't allow that to happen. AC motors. Okay. Synchronous motor, look familiar? It should do. It's the same as a three-phase AC generator. Also called a synchronous motor. Relatively low torque, good for constant speed applications. Might be single phase, this one's three phase, and they're not self-starting, or they're not self-exciting. The induction motor uses coils of wire inside. These are you're looking end on at the coils of wire, and if we were to go 3D view on that, you can see that the coils are like that through the armature. And this is the model you saw in the video there of for a generator, where you've got these rotating fields here and static fields here. What happens is the rotor chases the stator. It tries to catch up, but it can never get around the same production as the stator field, and the difference between the two is called the slip speed, just a term they use. Good for fuel pumps, hydraulic pumps, gyros, AC actuators, anything like that, induction motors. Alright, also called a squirrel cage motor, where you've got the solid bars here, and then you've got the coils around the outside of it. Now we saw the star connection. Delta connection is slightly different. So the delta connection, we've got the three phases there. The line and phase voltage are the same, but the line current is square root 3 of the phase current. So line voltage and phase voltage are the same, but the current varies. The way to remember it for a delta connection, the fact that the voltages are the same. Line current, as I've said, square root 3 of the phase current, or times phase current. Just remember V delta V. The delta connection, the voltages are the same. Line and phase voltages are the same. It's the current that changes. You're unlikely to be asked to calculate that. Be pleased to hear. Okay, so we've got AC electricity, we've got it turning motors, we've got it all sorted out with our reactance loads, our inductance and our capacitance. What are we going to do with that AC? Well, firstly, we can easily transform it to different voltages. With a simple winding of transformers like that, if you've got double the number of turns on the output side, you get double the voltage but half the current, because the relationship is constant. We can also have a thing called an auto transformer, where, as you can see here, if you've got a voltage here, you can take off 1, 2, 3 different voltages just by coming off a different point of the coil. They're fairly lightweight, so they're only useful for lighting or low current applications. Heavy current applications, you need chunky old transformer like that. Lightweight ones, auto transformers. What do we say, folks? Two. Why is it 2? You're right. Low current, so that's the first thing. It can't cope with high current. But a transformer can step up or step down. Yeah. Okay, diodes. A diode is, if you like, a one-way non-return valve for electricity. What you have is an anode and a cathode going in. This whole thing is just the casing around it, a resin case. Inside there, between the two sets of metal contacts, you've got 2 different types of silicon, N-type and P-type silicon. And the space between the two is lightly doped with boron or germanium, less common nowadays. If you've got too many electrons, then you'll get a flow Now this will allow a flow from N to P, but not from P to N. So the cathode will allow current to come down through there, but it won't allow it to backflow. So that's a non-return valve for electricity. The PN diode, which prevents flow PN, positive to negative, is the most common. But you can have the other way around. Depends on the application you need. So what you can do with that? Well, if you've got a diode, you've got the beginning of a rectifier. What you do with that is you take an AC output and you put it through a diode, and because it's only allowing flow one way, what you get on the other side is just positive peaks of electricity. You've binned the negative. You're not allowing those to flow back. So what you've done is you've actually rectified an AC current to a DC current through a single diode. It's a bit chunky, it's not a very smooth DC output, but it's an output. That would be a single phase half wave rectifier, just using a diode.
So we could use that between a battery and a generator.
Yes, you could. Yeah, it could be used in a protection device, yeah. If we want a cleaner output of DC from our AC input, then we use 4 diodes. And you can see from that that the flow would allow to flow through this way, but not that way. It would be allowed to flow this way, but not that way. So effectively what we're doing is we're giving ourselves all of those peaks of DC power. So that's a full wave rectifier using 4 diodes. If we've got a 3-phase output and we want to convert that, rectify that to DC, we've got to get a little bit more clever, and this time we use 6 diodes to give us a 3-phase full wave rectifier. You've got an awful lot of DC power right there, lots of peaks. So diodes, useful, give us our rectifier. If we put our transformer together with our rectifier, we get ourselves a transformer rectifier unit, which is very common in aircraft application. This isn't from an aircraft application though. Any idea what this could be from? On the left we've got a 240 volt AC supply coming in. We've got a winding there and we've got a winding there, so that's a transformer. So we're transforming it from 240 volts AC to a lower voltage AC. If we then put that sine wave AC through a rectifier, through a pack of diodes there, we get a 14 volt DC output. It's a battery charger. It's a car battery charger. But your transformer rectifier unit in an aircraft does exactly the same thing with 115 volt AC through to 28 volt DC. A TRU, a transformer rectifier unit.
Is that why sometimes on the battery chargers, on the actual gauge, you're seeing a slight, it's like we used to do a test where...
We're talking about car batteries here.
It was aircraft.
Oh right, yeah.
Tornado. And it was a test to see if the battery charge was working. And when you checked the gauge, you would see it doing that.
Right.
I think it's because, obviously, when you've got the peaks, you've got a capacitor in there, it rectifies it.
Yeah.
It's just slightly sort of changing the voltage.
Spot on. Yeah. TRU in the aircraft, something like that, it's just another box in the radio rack, isn't it? It's just another box of tricks. TRU. As well as normal diodes, you can have a thing called a Zener diode. Now, a normal diode, eventually, like any non-return valve, would break down because of the high reverse current flow. It's trying to batter its way back in. Eventually, a normal diode would break down. A Zener diode prevents reverse flow up to a point, and then it allows it. And once it's allowed the reverse flow, the diode voltage remains close to constant for a wide range of currents, which means it's ideal to be used as a voltage stabilizer. So a Zener diode is a voltage stabilizer. Symbol for it is the same as a diode, but with a stylized sort of Z on it. Okay, that's a Zener diode. There's a question about it in the bank? Yeah, number 1, voltage stabilization circuits. progression on from diodes is transistors. We see once again we've got a current flow right the way through there. This time we've got a sandwich of N material and P material, and again silicon or germanium doped between them. Now the idea of this type of transistor would be, if you think about it, it should work as two rectifiers. It should work as two rectifiers, and it shouldn't allow flow in either direction. But the doping is only quite light between these surfaces, so it does allow a percentage through. It's a weak P layer. It allows 98% of the electrons to go through. And then, when the other 2% build up in the P layer, it prevents any further electrons from crossing. So 98% has flowed through, and when 2% has built up in here, it just shuts it off. So in this case, the transistor is used as a switch, with a straightforward flow through like that. That can shut it off in about 50 nanoseconds. That's 10 to the power of minus 8 seconds, i.e. quite quick. Where you have this type of transistor, where you allow some of the electrons out to base, this time we allow one allowed out to base permits a further 50 to cross the NPN junction. So we allow one out and 50 cross. Percentage is the same, isn't it? 2% in that layer, 98% going through. But for every one we allow out, we allow another 50 across. So in this case, the transistor is being used as an amplifier to allow more electrons to flow through. And there's two types of these, NPN or PNP. The symbol for a PNP is that, and the symbol for an NPN is that. Nice easy way to remember it. Look at the arrow there, going to the emitter, pointing in, not pointing in. PNP, NPN. It's about all you need to know or understand about transistors. Certainly probably more than you need for the exam. Okay. Let's distribute some of this power around the aircraft then. We're going to have a split bus system looking remarkably like we saw on the split bus system for DC. We've still got a battery at the bottom. We've still got a battery bus bar and vital DC services. We've still got the essential services from the number 1 DC bus bar, and we've got non-essential from the number 2 DC bus bar. And they've got their own bus tie. So that's the DC taken care of. What we're looking about here is the 3 generators. We've got one on the number 1 engine, one on the number 2 engine, and one on the APU. And this little device here just shows us that the APU gen could power either bus bar. Number 1 then powering number 1 AC bus for non-essential services, essential AC bus for essential services. The number 2 gen, number 2 bus bar to non-essential AC. Both of those, number 1 is firing the number 1 TRU, transformer rectifier unit, to provide DC to the DC bus bar for essential services and to charge the battery. The number 2 is powering the number 2 DC bus bar for non-essential DC. And there's one little bit in between here. In the event that we were to lose all of the AC generation, we've still got a means of producing a tiny amount of AC power through an inverter from the batteries to essential AC services. Not unlike the diagram the examiner uses, although bizarrely they go for a complete inversion of the conventions. Conventionally you draw the generator at the top and then the loads flow down from it. Of course they put the generators at the bottom, because they would, wouldn't they? Okay. AC, how the batteries charged? Which one? 2. Transformer rectifier unit, TRU, yeah. Absolutely. Okay, parallel system with 3 engines. If we're going to parallel them, yeah, they must be in sync before joining. They must be completely synchronized in voltage and frequency and phase. Otherwise they just won't accept you being joined together. So the AC bus tie bar just ties the services together. Services are taken from number 1, number 2 or number 3, but the AC tie bar just ties those 3 together. Simple as. Generator control unit, much like we've seen on a DC generator. If we have a generator fault, then we've got an excitation breaker. If we break that, we are not now powering the excitation coils. We're not producing electricity. We also kick the generator off from the main bus bars, and that will protect for undervolts, overvolts, excess current, and under or over frequency. You can get as complicated as you want on these things. I mean, you've got a system there, look, 2 separate sets of parallel buzzes for a 4-engine aircraft, yeah, driving 4 generators and 2 APU gens. This is one system on its own, that is another system on its own. Remember, the AC tie bus bar is only there to tie the AC outputs together. Services are still taken from the numbered buzzes. Okay. One of the exam questions that comes up is like this, and you've got an example in your handouts. And this one, it's got 4 components blanked out. 1, 2, 3, 4. It'll ask you to identify from a list what a particular component is. And the list will be of things like generator control unit, inverter, bus tie, or a TRU. So in this one here, follow the flow. Just follow the flow from the generators, AC gen, yeah, powering an AC bus. So what must that component there be?
TRU?
Must be a TRU, mustn't it? Follow the flow. What about number 2? Component 2.
TRU.
TRU. Number 3 is also a TRU. What about component 4? That appears to go from the DC bus to the AC bus.
Inverter.
An inverter. Okay? So there we are. Nice and easy. Okay. Of course, when the labels are off them, it's a lot easier to see, isn't it? One of the questions comes up with the drawing with all the labels removed, and it'll ask you how you're going to get power from one point to another. Again, just follow the knitting, you know, follow the trail, and you can join it up quite logically then. Okay, and again, from that one drawing there, how many questions do you think you could write? So I'm not even going to try and give you a set answer to one question on that one. Copper indications. This is from an early type Boeing 737, but on this you've got on the left you've got the DC, which is amps and volts, and on the right you've got AC. You've got AC volts at the bottom, and rather quaintly you've got CPS at the top. Okay, cycles per second. Very quaint. And the rotary knob just controls what's going where. Really simple as that. This is the CDSU controller, again from an early type of Boeing 737. Dire warning, look, drive can be reconnected only on the ground. Once you disconnect your constant speed drive unit, there's no reconnection on this type until you're back on the ground. But really, all it's going to tell you is the oil pressure and temperature within there. Remember, it's a hydraulic system. It's 2 hydraulic motors running in there. That's your lot. This one is your AC generator load. 2 lots of AC ammeters really, and then just telling you where your buzzes are, whether the APU gen is on, whether the Gen 1, Gen 2 are on, and just follow the path through. Simple. Your TRUs giving you the amps that you're actually passing through the TR1 and 2, giving you the battery amps there, and your DC volts. And again, just selecting there as to what's powering what. Simple. A lot more simplified nowadays on the flight deck. Most of this is automated. There is no manual control of it. No need for it. This one is helicopter, boys. Charles?
Sorry.
No, know what it's from? What aircraft?
Oh, 22.
Yeah, R22, little Robbo. And you've got a huge amount of electrical controls there, haven't you? You know, you've got a battery master switch, you've got an alternator on and off. That's your lot. Then you've got amps up here and an alternator warning light. That's all you've got for your electrics on an R22. Gets a little bit more complicated when you get up onto a modern complex helicopter in this case. This is the schematic from one of the pages of the EVIS, where it's given you the 2 batteries, it's given you the generators, the buzz bars, the buzz tie, the voltages, the power outputs, everything. A little bit more complex. Overhead panel from a large helicopter. This is a 139. Again, just switchology. That's all you've got. Gen 1 and 2 and battery really. And you've got one big switch there that you can turn everything off in an electrical emergency. Just pick it up and bring the whole lot back. Let's just recap then briefly on generation of AC-DC power. An alternator generates AC initially, converts AC to DC with an internal rectifier. Typically used in most light aircraft and most cars will use an alternator. An AC generator does exactly what it says on the tin. It generates AC electricity. The output is AC. Can be single phase, can be 3 phase. Typically 3 phase AC 115 volts for an aircraft. DC generator, also known as a dynamo. If you've got one of those, the inverters will then convert DC to AC. A rotary inverter is a DC motor driving an AC generator, nothing else. And a static inverter is solid state. It works on the principle of PFM. Marcus?
Pure fucking magic.
You got it. Electrics. And we finished early. So I'll see if John wants to pick it up.